The dispute between Einstein and Bohr over the interpretation of quantum theory is a result of a deep conflict between two antagonistic worldviews. It created a painful split in the 20th century physics community. This fascinating battle was the greatest intellectual debate in modern physics.
It's a real battle. It's probably the biggest battle since the time of Galileo's and Copernicus against Ptolemaios. Namely, two worldviews are fighting each other, and one of them is going to win.
Einstein and Bohr's views were so radically different that they could not be reconciled. Einstein believed the world obeys objective laws of nature. Physical reality has a causal structure. Every effect has a unique cause. In principle, he argued, the world's underlying structure can be revealed by science. Bohr's opposite view was based on quantum theory. The laws of nature are indeterministic. A pure objective description of the physical reality is impossible. Contrary to Einstein, Bohr thought it meaningless to speak about the underlying objective structure of the world.
For Einstein, statistics was an objective property of a set of particles under a set of uncorrelated causes. While for Bohr, statistics is a final limit to human knowledge, and an observer can only predict with a certain probability of seeing a certain thing. That's all. And he can never understand the causal behavior of the world we are living in.
The major controversies in the history of science, Plato and Aristotle, Galileo and Ptolemy, Einstein and Bohr, have always been focused on the nature of physical reality. Two questions were at the core of the Einstein-Bohr dispute. Does the world have a causal structure? If the world has a causal structure, can science discern it? Bohr answers no, and Einstein says yes. In quantum theory, the physical world is totally chaotic or capricious. This is the essence of the quantum revolution. According to the uncertainty relations in quantum mechanics, the laws of nature are chance-like laws. Things happen in the quantum reality with no definite causes. Einstein did not accept this idea. In a world without causality, the sun can rise today but will not necessarily rise tomorrow. Therefore, Einstein argued, despite its success, quantum mechanics does not provide a complete description of reality.
Einstein famously said that God didn't play dice. I mean, he objected to the view that what happens in the physical world is the result of some irreducible chance, that God kind of throws the dice or spins the coin to see what's going to happen next. And Einstein seems to have felt that that was a very unacceptable aspect of God. I mean, this may be sort of connected with Einstein's ideas about theology and the nature of God. And somehow the idea of God casting dice and throwing coins and things seemed to be very objectionable to Einstein.
Einstein, I think, was a clear example of a Platonist. He believed that there were mathematical objects or structures in nature, and that there were simple, elegant equations which governed the behavior of those structures. He thought that even about quantum mechanics. He wanted a theory where the notation in the theory really represented the underlying, genuinely there, mathematical structures in the world.
Bohr's complementarity interpretation of quantum mechanics appeared in the fall of 1927 during the International Congress of Physics in Como, Italy. Bohr's interpretation was based on what he regarded as the essence of quantum theory, the quantum postulate. In quantum theory, Bohr argued, a sharp separation between the objects being measured and the instruments doing the observation breaks down.
That's why I always said we have to take the phenomena as a whole. A phenomenon is the combination of a measuring apparatus, which may be your eye, which may be very complicated machinery, tucked together with a quantum mechanical object. And the two cannot be separated.
Now, a blind man can be put into a room, and if he uses a rigid stick, he can find his way around and slowly build up a geometrical picture of the room that he's in. And in fact, it turns out that that room, his description of that room is very much the same as an ordinary man with sight would describe. Quantum mechanics for Bohr was very much like giving the man a rubber, bendy stick, so that he could not probe out the room sharply, because he could not say what was the object, what properties of the object he was touching was conveyed through the stick. And the stick bending and being floppy would not give him a sharp separation between his sensations in his hand and the object that he was actually probing. And so Bohr used that idea to try and illustrate this indivisibility of the quantum of action.
The quantum postulate, Bohr writes, implies an indivisibility of the observed objects from the measuring apparatus. The phenomena are a result of the interaction between classical measuring instruments and the quantum objects. The colors we observe are a result of the interaction between our measuring instruments, our eyes and brain, and the real objects existing in the world. We observe a hologram of a swan through a special filter. The hologram created by combined laser beams is a result of a quantum effect. As long as we continue to look through the filter, we observe the hologram. But if we move aside, the phenomenon disappears. So, does the figure of the swan exist independently of our observation? Bohr would answer, it does not. We cannot say that quantum objects exist independently of observation.
There are poets, who have described this Pirandello, for example. In Pirandello's Enrico IV, the characters, one of the characters says, I know that nobody ever will see me as I am because there is no I as I am, and I shall never see anybody else as he. So take all this together. There are lots of appearances, everyday common sense appearances, which indicate that there is whatever one observes is the result of a complex interaction where you cannot put a cut there and say, well, that is my contribution, and the other thing is a contribution from the object. But it has to be taken as a whole, like Bohr says with the phenomenon.
The world, says Bohr, is one indivisible block. The only way to describe phenomena in this whole is by means of complementary concepts. Bohr introduced the principle of complementarity in order to interpret the uncertainty relations in quantum mechanics. Heisenberg's uncertainty relations imply that quantum objects do not possess simultaneously all their potential properties. Therefore, a complete account of quantum phenomena requires contradictory descriptions which cannot be used simultaneously.
In order to describe elementary particles, you have various pictures or visualizable descriptions. Each one of them tells you what the particle does under certain circumstances. All of them together are needed to tell you the whole story, but none of them allows you to say that is what the particle really is in itself.
Roughly speaking, the idea of complementarity is that the way we describe the world is relativized to the mode of inquiry, if you like, the experimental apparatus and the context. Now, all these contexts have got to be specified in the language of classical physics. So you use classical physics to specify, as it were, the language of these contexts. And then the idea of complementarity is that you can't simultaneously get all the description of reality. In other words, it's a sort of many-faceted thing, reality. You can kind of look at one facet, and then you can look at another facet, another experimental arrangement. And all those descriptions have got to be in the language of classical physics. For this reason, as Bohr says, it's a language of objective communication.
So the position of Bohr was not very, very clear, but I think that in the position of Bohr, the fact that you cannot exactly separate both the measured system and the measuring apparatus, and the measuring apparatus and the observer and so on, in a sense, all this went together in his picture of the fact that the world is a whole, and of the fact that you can only put into evidence some of the phases of the many, many phases of reality.
Bohr's understanding of quantum theory rapidly became the orthodox view, what is later known as the Copenhagen interpretation of quantum mechanics. Einstein rejected Bohr's complementarity principle. He objected to Bohr's ideas that reality could not be described by objective and independent laws.
He didn't like this splitting of the world of the Copenhagen interpretation into two parts, the observed and so on. He insisted on the fact that we must look for universal laws.
Contrary to Bohr and the Copenhagen school, Einstein claimed that the indeterministic character of quantum mechanics was merely a result of human ignorance rather than a crucial feature of reality. During the late 1920s, Einstein constantly produced ingenious thought experiments to demonstrate that quantum mechanics was inconsistent or at least incomplete. Einstein designed his imaginary experiments to show that Heisenberg's uncertainty relations could not be valid as a fundamental principle of the physical reality.
So the Copenhagen interpretation for a considerable time was an inspired guess. And this inspired guess, why this inspired guess had so many followers, I cannot understand. One of the reasons was the result of the Fifth Solvay Conference, where the guys who argued against it, could not survive. Einstein brought one example, which was refuted by Bohr. De Broglie could not survive, so there was a kind of triumph, which then went over to the younger generation.
The Fifth Solvay Conference in Brussels in 1927 was focused on the most pressing problem in the interpretation of quantum theory. Is quantum mechanics a complete theory? The world's great physicists were present at that meeting. Bohr, Heisenberg, Pauli, and Born, the leaders of the Copenhagen school, argued that quantum mechanics was complete. Einstein, Schrödinger, and de Broglie, in the minority, claimed that the theory was incomplete.
In the morning, Einstein would come up fresh and cheerful with a wonderful counterexample against Bohr's view. He would explain the counterexample very quickly, very briefly, and Bohr would seem to be devastated. Then he would start with something entirely irrelevant. He would start talking, would move around, would come closer and closer to the example, and after a long time, the example would have been dissolved. Next morning, Einstein came again, fresh and ready to do battle with another counterexample. Bohr was again devastated. And again he would start talking from somewhere at the periphery, seemingly irrelevant, would move around in serpentines and epicycles, and then again the example would be dissolved.
Einstein is often accused of being reactionary, of not accepting the real revolution engendered by quantum mechanics. Having got one revolution going with relativity, people think there's even some inconsistency in the fact that in quantum mechanics, Einstein generally doesn't seem to go with the revolution. He's quite happy to give up Euclidean geometry, have strange new types of geometry when it came to the theories of space and time. But when it comes to quantum mechanics, many people think that Einstein in some sense was too much tied to classical ways of thinking.
Bohr regarded the statistical character of quantum mechanics as reflecting a real limitation in the human approach to nature. The classical demand for determinism, he argued, must be relinquished. Einstein's group strongly objected to the idea that nature obeys statistical laws. They argued that hidden variables existing in reality are missing from quantum theory. Classical Newtonian physics explains every effect in the macroscopic world by a hidden cause. Gravity is the hidden cause forcing snowflakes to fall on Earth. The situation must be similar in the quantum world, Einstein's group argued. Had we known exactly the hidden parameters, the veil which covers reality would have been revealed. The fundamental problems of action at a distance and indeterminism in quantum theory would have been resolved. Einstein, de Broglie, and Schrödinger's view was totally rejected by Bohr and the Copenhagenists. The dispute, however, was not concluded.
they really had no way of settling the issue. You see, Bohr felt that he had solved the problem raised by Einstein, but Einstein didn't, because they had different notions of what is meant by reality. You see, Bohr said there may be some reality, there is, but this reality must be unambiguously related to certain phenomena before you can talk about it meaningfully, whereas Einstein said you could talk about it without knowing how to measure it all at once, right? And Bohr answered back that this was ambiguous because you could not say what it meant. But Einstein took the opposite attitude, saying you begin with the theory to see what can be observed, and Bohr said begin with the measurements to see what the meaning of your theoretical concepts is. Now, they had different notions of what is meant by reality, and they couldn't meet.
Despite the success of the Copenhagen interpretation, Einstein did not withdraw from his attacks on quantum mechanics. In the early spring of 1935, while at the Institute for Advanced Studies at Princeton, Einstein, together with Boris Podolsky and Nathan Rosen, published an ingenious argument against the completeness of quantum mechanics, and in particular, against the general validity of the uncertainty relations. In their argument, EPR as they are called, imagined the following experiment. A common source emits twins of particles in opposite directions. The particles fly apart toward measuring devices that measure their spin value. For simplicity, we may imagine the spin property as if the particle rotates around its axis. In this experiment, if the spin of the left-hand particle is measured to be up, then the spin of the right-hand particle will also, with certainty, be up. The same happens if the result of the measurement is down. This is strange, since we know from quantum mechanics that the result of a spin measurement might be either up or down for every individual particle. Yet in this experiment, we find that the spins of the particles are always identical. This strange correlation between the particles is called quantum entanglement.
The difficult situations come when the two microscopic parts of the system are far apart, each from the other. In this case, due to entanglement, there is a sort, in suitable conditions, there is a sort of influence of one part on the other, even if they are far apart so that they do not interact.
Even when the left-hand particle is measured before the right one reaches the measuring device, the spin states of the particles are always identical. The correlation occurs although the experiment is designed in such a way that no influence or connection whatsoever exists between the two sides of the apparatus. The crucial question put forward by EPR is this: what is the reason for this correlation? How does the right particle always manage to match the spin state of the left one? It seems that a non-local interaction, faster than the speed of light, a ghost-like action at a distance, is taking place in quantum mechanics. And this, Einstein argued, is definitely impossible.
If you can observe something without disturbing it or participating in it, and observe it with complete accuracy and probability unity, then that must be independently real. You know, that was Einstein's idea. It seems it's a common sense idea, actually, that if something could be observed without disturbing it with perfect certainty, then it must be real.
So what Einstein is saying, you make these predictions with these two spin systems, and by measuring what's on this spin system, you can predict exactly what the measurement's going to make on that. And therefore, according to his criterion of elements of reality, there must be something in reality that's actually there before you make the measurement corresponding to the spin being down. In other words, if you predict the spin's down, then it must actually be down before you make the measurement.
In this experimental situation, EPR argued, an observer is free at his whim to measure either spin x or spin y of the left-hand particle. If the observer were to measure spin x of the left particle, then whatever the result may be, the x spin of the right one can be predicted with certainty, since the particles are correlated. Nevertheless, the observer could decide to measure spin y of the left-hand particle instead of spin x, and so he could predict with certainty the y spin of the right particle. Therefore, EPR argued, there exist objective elements of reality, corresponding to the simultaneous existence of both spin x and spin y of the right-hand particle. The problem raised by EPR is that according to the uncertainty relations in quantum mechanics, the simultaneous existence of spin x and spin y is impossible.
Before the experiment was done, I know I could observe the position of the particle A, and then particle B would be determinate. I would do so without disturbing particle B. Therefore, there must exist in particle B some element of reality which corresponds to the position. And similarly with the momentum. I could observe the momentum. So he said that there ought to exist in particle B something corresponding to position and something corresponding to momentum, both defined together simultaneously. Nevertheless, according to the quantum mechanics, this is impossible. You can only define one or the other. So his argument was that quantum mechanics was incomplete. There is more to it which would determine these things, but quantum mechanics has an incomplete description that would be only statistical.
The crucial point is that an exact simultaneous prediction of both spin x and spin y in this experiment contradicts Heisenberg's uncertainty relations. Therefore, the EPR thought experiment totally demolishes the very essence of quantum theory. Thus concluded Einstein, Podolsky, and Rosen, since we reject the possibility of faster-than-light interactions, quantum theory is definitely incomplete.
Therefore, this was a blow to Heisenberg. And then it implied that you had a faster-than-light correlation, interaction between the two particles. Ah. Now that's very, very astonishing, of course. This raised fantastic problems.
The best explanation for the correlation at a distance implied by EPR is the existence of common causes or hidden variables. These hidden causes, absent from quantum theory, determine the spin states of the particles for any future experiment. The correlation between the particles can be simply explained by assuming that the twins originated in the source were produced in exactly the same state. During the production process in the source, twin particles are born with the same genetic code for every spin measurement, x and y. If an observer were to measure spin x of this twin, then the result would have been down for both particles. The down state for spin x is already determined in their genetic code. If instead the observer were to measure spin y, then for this twin, the result would be with certainty up. This genetic code of the twin particles predetermines the results of any spin measurement in the future. The problem, argued Einstein, Podolsky, and Rosen, is that the genetic code is missing from quantum theory. Therefore, the theory is incomplete.
Einstein, Podolsky, and Rosen thought that you could not escape to this notion of common causes, and so that you have to supplement quantum mechanics with these hidden variables, or common causes. But at that time, they did not know that in fact hidden variables, common causes, are incompatible with quantum mechanics. And probably Niels Bohr felt that it was incompatible, but he could not demonstrate it.
Bohr rejected the EPR argument. He argued that simultaneous elements of reality exist only when they can be simultaneously measured or predicted. In the EPR experiment, this cannot be done. Measurements of spin y on one particle change the predictions regarding spin x of the other one, however remote.
Essentially, his answer was that it would make no sense to discuss what a result could have been if you had measured it when you didn't actually measure it. Right? If you take particle B and ask what properties it had because it could have been measured, that's not enough. You could only discuss the property it actually had when you measured one, either position or momentum, so that this problem would not arise.
And so he simply rejected Einstein's argumentation on the basis of what you could do if you did such and such an experiment. And Bohr thought this wasn't the right way to identify elements of reality. You've got to specify the exact experiment you were doing. And in the context of that experiment, then certain elements of reality could be said to exist. But if you did some other experiment, or asked the question, does this element of reality continue to exist in a situation where I'm doing another experiment, which I might have done, Bohr says, no, that's absolutely wrong. you've got this element of reality, you go and do the other experiment, this element of reality just goes out of existence, as it were. And therefore, changing the experimental context, Bohr didn't think was a kind of unacceptable action at a distance or influence. It was more a question of bringing things into a state of being well-defined, which he thought was quite different from some physical effect of making something change from one element of reality to another. And so the argument really hinged on this question of whether the EPR, understood in Bohr's terms, did involve action at a distance or not. Einstein saying yes it does, and Bohr denying it.
Niels Bohr and Albert Einstein's conceptions of physical reality were radically incompatible. Bohr's world was chaotic and contextual. Einstein's world was harmonic and objective. Their irreconcilable worldviews led to a deep personal split that lasted till the end of their lives.
When Einstein, the Einstein-Podolsky Rosen came out, Pauli wrote a letter to Heisenberg. The Pauli letters are slowly being published. It's gone up to the 20s or something, you know. He said, Einstein once more has uttered himself on the quantum theory. If a graduate student in one of my physics courses had put forth this argument, I would think he has some amount of intelligence.
Einstein never felt that he won. I mean, Einstein felt that he was avoiding the question, right? He called it a tranquilizer philosophy, a gentle pillow on which he could rest his head. So Einstein simply felt that Bohr was not listening to him. And he may have been disappointed that other people were following Bohr, but even those who followed Bohr didn't really understand him very well.
For the next 3 decades, the Einstein-Bohr dispute gradually faded. It was only in 1964 that Irish physicist John Stuart Bell discovered one of the most surprising theorems in 20th century physics. Bell's theorem proved that a crucial test between Einstein's hidden variables approach and Bohr's complementarity interpretation is experimentally possible.
Now, as a consequence of the work of Bell and the work of Aspect, the situation has changed. We know that Einstein and Pauli were both wrong. The question with which Einstein attacked quantum theory are correct questions, but the answer that Einstein was expecting are not the correct ones.
It's a great irony. Bell was an objectivist. He wanted to have an objective reality. He regarded Bohr's point of view as very irrational. As a matter of fact, he said that he couldn't understand at all Bohr's answer to Einstein. And Einstein, he said, I mean, these are his own words, was the rational man, but unfortunately, the rational man was not right.